Hello everyone. I hope this is working. It's been a while since I've done a YouTube video, but I am going to start doing YouTube videos. I'm going to concentrate on a few of the math as far as calculus goes. I'll probably work on some calculus, maybe a little bit of pre-calculus, maybe a little bit of algebra 2. Maybe a little bit of college algebra, whatever. But I am, by the way, KP the Math G. And in this video, I'm going to show limits graphically. And so, of all the things that we discuss in calculus, we begin with limits, and then from there, the derivative that comes from the limit. And then we go in reverse order. We do the antiderivative and the definite integral. And so we're going to take a little bit of this one step at a time. So we're going to start with showing limits graphically. I have a few examples that I'd like to share with you this time. And that is, let's take a look at the XY coordinate plane, and let's kind of talk a little bit about, let's put some numbers up here. Okay, bear with me just a little bit. I probably should have this drawn out before recording, but it's okay. Okay, we're just going to make this. Okay, so let's see if we can draw a function, say, of f. So let's see, we're going to do something that looks like this, going right through here, and then somewhere right in here, we're going to come down to about right here, and then come down to about right here, and then probably right about here, okay, and then somewhere just shoot this off like this. Okay. Alright, so this is a function. We're going to call this a function of f. Okay, we could have called it g or anything else. Okay, speaking of g, I could be the math guru, which I don't know if I'm really a math guru or a genius, or even as some of my former students have called me, gangsta. Yeah, gangsta with an A on the end. Okay, so yeah, the math, you use G whatever you want it to be, but we're going to call this a function of f. Okay, and first of all, when you're dealing with limits, first of all, you need to find out maybe what f at some number is. Okay, for example, f at -3, the x value will be here, the y value will be right there. Okay, so whatever the y value is, so we know that that is at 0. So f at 3, or -3 rather, is 0. I kind of designed this, f at -1. Okay, I wanted it to appear to be at 2, so f at -1 is 2. Now this is not a limit, this is just f at some, this is the x value, this is the y value. Actually, you can rewrite this as -3, 0 if you want to. This one would be -1, 2, okay, like that. That's what it is. It's f at some number, f at some x equals some y. Okay, of course, look at this. We have, obviously, here's f at 0, which is 0. We also have another one that's at 0. It's 2. Alright, f at 2 is also 0. Actually, we got 3 of them. So f at -3 is 0, f at 0 is 0, f at 2 is 0. I just kind of designed it that way. It looks as if f at 1, we're just kind of going through this a little bit, is -1, isn't it? All right, and there again, we could write it as 1 comma negative 1 like that. Okay. This is the point 1 comma negative 1. Okay. This is not an interval from negative 1 well, negative 1 to 1. It wouldn't be written correctly anyway. The negative 1 would have to come first. But this is a point 1 comma negative 1. Okay. Point negative 1 comma 2. And sometimes in calculus we get that confused, that we're going from negative 1 to 2. That is not true. This is a point negative 1, 2. So f at negative 1 is 2. That's just another way of writing it. So you need to be familiar with f at, generally speaking, f at a is equal to some b. Okay, the x value, oh well, sorry. Okay, the x, we might call this x1, we might call this y1, whatever. Okay, so this is the way it is here. Alright, so you need to be familiar with that kind of language here. Alright, let's erase this. My wife got me this board for my birthday. Okay, and I'm very pleased to have it. And so I'm hoping maybe I can use it frequently and show you a few things, hopefully. I hope there's not a glare on the board. I tried to get rid of, I had too much lighting a while ago and it was showing a glare, so hopefully this will be okay and hopefully it's not too dark and you can see fine. Okay, let's do another one here. Now let's get a little bit more into the limit. Okay, and again I probably should have had this already drawn out, but we'll try to be a little brief with this one. Okay. I don't know, I'll put a 3 here and decide I want to put a 3 right there. I don't know. Alright, now then. Here we go. We'll put a negative 3 right here. Okay, this is a rough sketch, as you can tell. Okay, so, excuse me, let me draw another picture here like this. It's going to be probably a little, maybe a little parabola here. Okay, so right here. We'll go through here and then maybe come up to here. We're going to make this a hollow circle right here, and let's go up to 3 right here, and let's put a solid circle right here just above that, and we're going to come down, well, it doesn't matter, and we're just going to do that. Okay, so we'll call this a function of g. Doesn't matter, we could call it g or f or anything we want it to be. Okay, so we can begin by saying, well, g at negative 1 is 0. Now, when we come to the limit, when we think about a limit, we want to consider the left side and the right side. And so, let me kind of do this for you. Okay, this is going to be like a vertical line here. It's imaginary, you can't really see it, so let's just do this for right now. Okay, alright, one more should do. Alright, to the left, this goes on and on and on forever and ever, but to the left of this, you might say that the domain is from, well, we're looking at from negative 1 to infinity this way, to negative infinity actually, and then from negative 1 to positive infinity would be the right side. So this is the left side. So if we had somebody walking along the x-axis, okay, like this, okay, I'm not a very good drawer, so if this person could look down, could he see graph, he or she? Yes, there's graph over here. Okay, so as long as there, and then we're looking at this limit, and this is how you say limit, L-I-M, okay, and we're looking at the limit, and this person is on the left side of this dotted line. You see that? This is the left side of the graph. Okay, so the limit as x approaches negative 1, and we always say from the left. We put a negative sign right here, and we just say, oh, it's not F, it's G. Oh my, okay. G at X here, not F. This is the limit as X approaches negative 1 from the left. Okay. Well, obviously we know that G at negative 1 is 0. If we were to get to negative 1, we would run obviously into 0. So the limit of this is equal to 0 from the left. Okay, this is called the limit from the left. Okay, well, let's erase our figure and put the figure, this one to the right. Well, let's put it over here for right now a little bit. Okay. Alright, so this person is coming from the right. We don't care how far from the right this person is going, but eventually this person is traveling in this direction toward negative 1. So in this case, we're saying then this is a limit. Let's put it over here. This is a limit as X approaches negative 1. And I wonder if you can think, if the left side is a negative sign, what would be the right side? From the right would be positive. Okay, so, and this is G at X, of course. And do we get there? And then this person going this way, going this way, going this way, and finally, yeah, at negative 1, they see 0. They run into 0. So look, right here, this is also 0. So what we're saying is, we're looking at limits from the left, limit from the right. The reason we do that is we want to find out if this limit exists. If the limit, there's a rule that says that if the limit as X approaches some number from the left, let's call it G at X this time, equals the limit as X approaches, A from the right, G at X. If they are equal to each other, then we say that the limit as X approaches A, some number A, without a plus or a negative, G at X exists. Okay, it does exist because the left limit, we say the left limit is 0. The right limit is also 0. So this is the left limit, left hand, we might say left hand limit is equal to 0. Yes, it is. So limit from the right, let's say the right side limit, or the right hand limit, remember how you want to say that, is also equal to 0, then the limit itself equals 0. That's how you do that. Alright, so that's the rule. If the limit from the left equals the limit from the right, then the limit does exist. Now, let's get to this thing here. Okay. Oh, by the way, let me erase some of this. Let me get this out of the way. Alright. I'll try to be brief. I'm slow at erasing, so please bear with me. I'll erase this. Alright, so let's see here. Right. Oh, let's leave that there. All right. So, okay. So this has a hole in it, doesn't it? This looks as if G at 1 does it. And this is a lesson on actually what we get into later on, continuity. Is this graph continuous? Well, it has a hole in it. Okay. So if it has a hole, it's kind of like if somebody were to walk up this hill and just keep on going and ignoring the hole, they would just fall down. And if they walked up on this side, they would fall down. And so in this case, we're saying that G at 1 does not exist at 2, but rather the dark. See, this is a hollow circle. We want the dark circle. Well, G at 1 is equal to 3. Okay, now let's look at this limit and say, well, this hole is here, so the limit must not exist, right? Well, okay, let's ask this question. Let's look at this limit. The limit as x approaches 1, now remember from the left, and we're talking about the function of g. That's still a function of g. Okay. Oh, by the way, let's move this over here. Since we're looking at 1, like this. Okay. And maybe let's put 1 or 2 more right here. Okay. There we go. All right. Now, the question is, if we know if this were a solid circle, we know that the limit does exist because it exists just like it did here. This was 0 from the left, 0 from the right. In this case, it's very simple to see this. This is 2 from the left of 1, okay, and also 2 from the right of 1. Obviously, if it's solid, it's going to exist. Okay, but what if it's hollow? And you got this G at 1 equaling 3 here. Does the limit still exist? And the answer to that is, if you walk up this hill here, okay, do you approach the hole? Even though it's a hole, do you approach the hole? Okay, the answer is yes. So yes, the limit from the left does exist. The limit is 2. Even though G at 1 is 3, the limit is still 2 because you're treading along the line itself. This is off the curve. This is on the curve. And when you look at limits, you want to look at the curve itself, not at the point somewhere off the curve. You want to look at whether it's a hole or a solid place. Okay? So, yes, this is 2. So if you come up here from the right, and remember we say the limit as x approaches 1 from the right, g at x, do we run into the hole? Yes, we do. We run into the hole. Now, we don't want to step into the hole, but we approach the hole. As we're approaching 1, we also approach that y value hole right there. All right, so yes, it is at 2. Don't be confused. G at 1 is still 3. That's the solid part. Okay? All right? But the limit is where the curve is, and we can easily see if it were solid, there would be no discussion here. But even if it's hollow, it's kind of like reaching a, all right, so we reach a bridge, but the bridge is gone. Okay, in Heber Springs they have a place called the Swinging Bridge. It used to be there. It's gone now. But at least if I approach the bridge from one side of the river and approach the bridge from the other side of the river, I still get to that empty spot bridge, even though there's no bridge there anymore. I get where the bridge used to be. I approach that spot. So now, probably at the 1 mile marker or whatever, I still get to the hole. Maybe this is a volcano mountain here, like Mount Fuji that we saw this last summer. you still approach the opening from the left, you still approach the opening from the right. So still either way, you're, okay, so if this is 1 mile, boy, this is 2 miles high, isn't it? Pretty high. Okay. If it's 1 foot, it's probably not a mountain anyway. 2 feet, not a mountain, probably a little bitty molehill. But anyway, you still approach this hole here, don't you? Okay, so yes, the limit exists. That's my point. Okay, 1 from no negative, no positive. G at x does equal to, so the limit does. Therefore, that means therefore the limit as or at as x ROA approaches 1, okay, from either side exists. And this is actually the y value, isn't it? So at y equals 2, okay, want to say that? Okay. Alright, so don't let that confuse you and say, oh, there's no limit here. Well, if you had this dot removed right here, you would not have g at 1. G at 1 does not exist. We say D and E does not exist. But just because it does not exist does not mean that the limit does not exist. Okay? We still have a hole. Even though it's a hole, you still can approach the hole from the left or from the right. And if you can get there, either way, yeah. Okay? Alright. One final thing is, let's find one that where the limit does not exist. Well, we are going to leave this here. Okay? Alright. I'm going to erase this part right here. And I'm going to put something, you've heard of a piecewise function, haven't you? This is still a function of g. This is g from the left. This is g from the right. Okay? So does elf at g, does elf at 1, or g at 1 rather, exist? I keep wanting to say elf all the time. Okay. Well, let's see here. Yeah, g at 1, or actually does exist in this case. It's not here, remember, but where the solid part is. At 3. Okay, just like that. Alright. Negative 1 from the left is this hole right here. It's 2. But from the right, if you come from here going this way, from the right side, okay, from the right side of this dotted line here, you run into 3. Well, okay. So, what we have here, what can we say about the limit? The limit as x approaches 1, g at x. Is it 2? Is it 3? It's 2 different answers, isn't it? So, being that it's 2 different answers, I don't know, E and E does not exist. Because, well, from the left it does, from the right it does, but it doesn't meet at the same spot. Okay, so like unlike the last one, remember, we're going to dot it. It approached from the left and from the right. Remember, it approached the same open circle, didn't it? But here, the left side approaches the open circle, but the right side approaches the closed circle, which is above that by 1 unit. So if this is the case. So here's the rule. if the limit as x approaches a, well, let's call it g at x, let's say from the left, is not equal to the limit as x approaches a from the right, g at x. What's the conclusion? The limit as x approaches a, g at x, does not exist. Okay, there you have it. So we've looked at what g of a function is, alpha of a function is, whatever. We wanted to do that because later on we're going to talk a little bit about continuity, probably in the next lesson. Actually, you can tell that these are not linked together, so the function of g, since the limit does not exist, obviously, okay, well, in this particular case, the limit does not exist. Well, then that means we have a discontinuity here. There's a gap here. So, in other words, but we'll have to look into that too. Now, there are 3 rules that we'll have to look at next time, but we'll get into that in another lesson. This is the lesson that we wanted here. G at 1 is equal to 3. Alright, so sometimes the limit does exist. That means that both of these numbers have to be the same thing for this to be no D and E. But since the numbers are different here, it is D and E. Okay? Does not exist. And that's the lesson that I wanted to portray to you. I know that's a lot to swallow because we talked about a limit from the left, a limit from the right, all in one lesson. So anyway, be that as it may, I hope this has helped you, and good luck with your studies in this. I know that you're being almost November, that you are well ahead of this, but this may be a good review for you at this point. Okay, y'all have a good day. Coming from KP, the Math G. Have a nice evening. Okay, goodbye.